lot of students today.
Yeah.
Okay, so good afternoon. I'm very pleased to introduce today's speaker, who is Chenyun Dai. He's a senior PhD student at the CS department. He does a lot of research on data security.
Thank you very much. Hello, everyone. Today, the title of my presentation is Privacy Preserving Assessments of Location Data Trustworthiness. So before we start everything to discuss everything in details, let me give you an example that motivates our research work. So suppose you are a police department officer and you want to invest a crime, and you know that the crime scene. So in this example, it's at location Y. So we have still three locations: location X, Y, and Z, and Y is the crime scene, which we are interested in. And we have three suspects, namely Alice, Bob, and Carol. And we have observations that they were in location X at 1 p.m. at a certain day. And we also have some observations. Our witness says that Alice and Carol is at the crime scene at location Y at 2 p.m. And another observation that Alice and Carol is at location Z at 3 p.m. However, for Bob, we don't really have its observation at 2 p.m. So Bob reported that he's at location Y, Y prime at 2 p.m. by himself. And we also observed that Bob is at location Z at 3 p.m. So our question is, we don't have any, we cannot verify that Bob's location at 2 p.m. And our question is it true that Bob is at Y prime at 2 p.m. as he reported? So if we can get some other information, for example, in this example, we get a piece of anonymous data from a traffic management system, which is in red trajectory in this example. So suppose we don't have any other, moving objects, moving individuals in this area, we can have some conclusion that one of them, although those data has been anonymized, so we cannot really see the identity of each trajectory in this example. We can still conclude that one of the trajectory may be Bob's, and Bob is possibly in the crime scene at that time, and the location Y prime reported by Bob himself may be wrong. So any questions so far? So our question is, how can we make use of anonymized data? We use two approaches. One is called common pattern analysis. The reason that we want to use common pattern analysis is that typically the anonymized data is available in very large volumes. So although during the anonymization process, some data may be modified to fulfill the requirements of privacy, the movement patterns can still be properly estimated because those data is available in large volumes. And another approach is called confluent support analysis. So in this analysis, what we tend to do is to link the one of the trajectory in the local data sets of exact information with the remote data set of anonymized information. So in other words, we want to kind of make a one-to-one mapping between the local data set to the remote data set. And our goal is to refine the trustworthiness assessment using anonymized data. So this figure shows the system architecture of our framework. So basically, the law enforcement agency possesses a local data set, and it is able to compute trustworthiness of its local data set. When he wants to verify its local data set, it sends queries to some remote parties. In this example, it's a GSM server which records the cell phone user's location, and another remote party is the traffic management system. So after receiving the queries from the law enforcement agency, it returns anonymized data to the law enforcement agency, and then the law enforcement agency try to use the remote data to compute the trustworthiness of its local data. So one thing to keep in mind is that since the remote party only returns anonymized data, so the privacy of the individual who use the cell phone services or use the traffic management system can be preserved. So one key component of our work is the privacy model. We didn't develop our own privacy model. On the other hand, we use an existing privacy model proposed in a paper in ICD 2008. The name of the paper is Never Walk Alone. So let's take just let me introduce briefly how the model works. So, so does everyone know what is k-anonymity? Who knows k-anonymity? Okay. Okay, let me just give you a brief introduction. What is k-anonymity? Basically, it means that if we form a group of k members, one of the member in this group cannot be distinguished from the other k-1 members. So that's the basic concept of k-anonymity. So for example, in this example, we want to form a 2-anonymity group. So what should we do? So first thing is that we choose a trajectory T1, and we find the closest trajectory to T1, which is T2 in this example. Then we compute the mean trajectory for these two trajectories and produce a bounding tube of diameter delta. So delta here is a user-defined privacy parameter. Or in some publications, it's a parameter which determines uncertainty. So what does this parameter mean is that if two trajectory is within a bounding tube of diameter delta, it is considered that those two trajectories cannot be distinguished with each other. So in this example, the next step we need to do is to do a space translation. We move anything outside of the bounding tube inside the bounding tube. So if you see this space translation, basically we move actually 4 points here to form this two anonymity set. So here we can see that a 2 delta set is created. So any questions so far? Okay. So so next step I want to introduce you the common pattern analysis procedure. So we have a few definitions to introduce. If we have 5 individuals at time 1 p.m., at time 2 p.m. They move to another location. Then at 3 p.m. they are at other locations. So we say those traces formed by the individuals' trajectories. We call them trajectories. And for the location associated with each timestamps, 1 p.m., 2 p.m., 3 p.m., we call them positions. And we classed those data so that positions which are close to each other will be formed clusters. And if the successor of a movement and if a predecessor of a movement and successor of a movement are within the same cluster, we will call it group of movements. So in this example, we will have 4 group of movements. And within each group of movements, if the start time and the end time is close to each other, we said that we call them patterns. Basically, if the pattern is common, then we call it common patterns. So in this example, although we have three movements in a group of movements, since they have different start time and end time, we only have two patterns. So let me give you an example how we use the common pattern analysis to compute the trust scores. So for example, we have that many positions in the local data set. The first step is to class those positions. After that, after we get the remote tubes from the remote data set, we continue our clustering procedure by injecting those remote tubes to the existing clusters. And we discard the remote tubes which are too far away from the local clusters. So you will see that we have 6 remote cluster tubes, but after we discard 2, we only have 4. After that, we will consider group of movements. So if we want to compute the pattern in purple in this example, basically 3 purple movements from cluster C1 to C2 and start from 2 p.m. End at 4 p.m. First thing is that we compute K, which is the group of movements from which PT is chosen. In this example, we have actually the size of the group of movement is 5, and we also compute K prime. K prime is the movement which contains in K and contains only local movements from C1 to C2. So in this example, it is actually 3, I think. We also need to consider other group of movements starting at C1 and C2 and starting at C1. So we see that there are 3 group of movements starting at C1, which is G1, G2, and G3. And we computed the GI prime, which contains only local movements. And also we need to consider group of movements ending at C2. In this example, it's H1 and H2. Again, we only consider the HI prime, which contains only the local movements. So in the end, we use this equation to compute the trustworthiness of this pattern. So the intuition behind this equation is that basically we want to compute the common pattern, right? So to compute a common pattern, we need to consider whether so basically this pattern starts from C1 and ends at C2. We need to consider all the movements, all the patterns start from C1, and all the patterns end at C2. So if the movement from C1 to C2 is the majority, we definitely need to assign a high score to this pattern. If it is not, we will assign a low score. That's the reason we want to consider the group of movements like G1, G2, and G3, and H1, H2. The reason we only consider the local movements when we do this computation is that so if there's a remote data set supports the current pattern that we want to compute, in this example it's PT, we want to increase its score. We don't want to reduce the score of because we already see and support. We don't want to reduce its score. That's the reason when we do the division, we only consider the local movements. So the next, so any questions for the common pattern analysis? So the second approach I want to introduce is the confidence support analysis. still some definitions. So when we say two positions support each other, we need to consider a threshold. So if we have two positions, PA and PB, which belongs to two different trajectory and shares the same identity ID, you can see that OID is the same. And if TA equals to TB, which means they share the same time stamp, and uh, the distance between PA and PB is less than 5, then PA and PB, we say PA and PB support each other. Otherwise, if they their distance exceed the threshold, we say PA and PB conflict with each other. So another definition I want to introduce is the distance between two trajectories. If two trajectories T and T prime defined in the same time span, which means that for each positions in these two trajectories, they have the same timestamp. They have the same pair of timestamp. We use the average distance between each pair of positions of T and T prime as the distance between these two trajectories. So this example actually shows what is conflict and support. So if we have conflict support threshold 5, and we have D1, D2, D3, and D4 for distance. So D1 is less than 5, so P1 support P1 prime, and same for P3, P3 prime, and P4, P4 prime. However, D2 is greater than 5, so P2 conflicts P2 prime. And the average distance between these two trajectories is the average distance is the distance of D1 add to D4 and divide by 4. So the next step is to do a mapping between the local trajectories to the remote trajectories. I will show you what is the difficulty in this problem. So suppose we have 4 local trajectories, L1 to L4, and we have 3 remote trajectories, R1 to R3. Then, so if we start from a specific trajectory, in this example, L1, and try to assign the closest trajectory to L1, let's see what will happen. So since R1 is the closest remote trajectory to L1, so it will be mapped to L1. Since R1 is already taken, L2 can only map to R2. And since R2 is taken, L3 will choose the closest available closest trajectory, which is remote trajectory, which is R3. And L4 will map to nobody. So this is the map that we get if we will start from L1 and try to find the closest trajectory for each one. So, but you can see that obviously it's not a really good mapping, right? Because L1 is really far from R1. So a good mapping will be something like this. L2 map to R1, and L3 map to R2, and L4 map to R3. So it's a much better configuration in this example, and we leave L1 map to nobody. So if we use a greedy method, we can get this configuration, which means that every time we take the closest two trajectory which is closest to each other at each time. However, even we use a greedy method, it may not work every time. For example, in this example, the closest will be R1 to map to L2. So if we take this as we assign R1 to L2 first. The next step, we can only assign L1 to R2. Then again, this is a very bad mapping because we can easily find a better mapping, something like this. We map L1 to R1 and L2 to R2. Although the closest remote trajectory to L2 is R1, but on average, it's the second configuration is a better mapping. So to do that, we introduce basically a cost. The cost is if between two trajectory, if the average distance between L1 and R1 is less than 5, then it will be the average distance between these two trajectories. If it exceeds, and if we exceed 5, and then it will be some default value we set to max. So formally, this is the cost function we use in our research work. So basically, if two trajectory, the average distance between two trajectories is less than 5, then it will be the average distance itself. If it's greater than 5, then it will be a W, which is a default value for max distance. And if you can see from previous example, the number of local trajectory may not be the same as the number of remote trajectories. So if we need to introduce some dummy trajectories in the remote data set, basically T is mapped to the local trajectory T is mapped to a dummy trajectory, then the cost will be W again, basically because we don't have a map for T. But if the number of remote trajectories is greater than the number of local trajectories, then some of the remote trajectory may not get a map. So at that point, if T is dummy, then the cost will be set to 0. And then we can basically convert this problem to the following problem. Basically, we want to minimize the cost to provide a configuration which is define a one-to-one mapping correspondence between local and remote trajectories. We can have a cost, and our goal is to minimize these costs. And again, we can convert again this problem to basically, once we have the cost function, we can build a matrix, and then our problem will become something like this. And so Xij will be the basically if it introduce I corresponding to the trajectory belongs to the local data set, and J belongs to the remote data set. And we have the constraint that xji equals to 1. What does it mean? It means that every local trajectory can only map to one remote trajectory. And the sum of xij equals to 1 if I belongs to local trajectory. That means that a remote trajectory can only map to one local trajectory. And x is either 0 or 1, means it either maps to a trajectory or it doesn't map to a trajectory. So cost ij is the elements in the ith row and jth column of the cost matrix. For this problem, there already exists an order n to the 3 algorithm, which is called Hungarian method, that can solve this problem. The Hungarian method actually already exists, I think, for 100 years, so I'm not going to go into details for this Hungarian method. So let's take a look at this example, which will show you how it works. So in this example, R4 is introduced dummy nodes in the remote dataset because we have 4 local trajectories and we only have 3 remote trajectories. So if you can see from this matrix, uh, all the uh, all the cost all the costs from L1 to R4 is all 10 because 10 is the default maximum value. And L1 to R2 and R3 are also 10. Why is it? Because the phi is set to 0.6. So the distance between L1 to R2 and R3 exceed this threshold. So they also set to 10 as the maximum default. And we want to compute the total cost. And this cost function has this constraint. After running this Hungarian method, we will get this set of mapping which satisfy this constraint and with the minimum cost. So here the minimum cost will be 10.3. The result will be L2 mapped to R1 and L3 mapped to R2 and L4 mapped to R3 and L1 will map to a dummy node. In other words, it will map to nobody. So we have a mapping here. Basically, we build a link between the local trajectories and remote trajectories. Then how we compute the trust scores for the confidence support analysis. So we assume that initially we assume that all the trust scores, no matter it is a remote trajectory or a local trajectory, it's all 0.5 because we don't have any opinions on that. So then we use these two equations to adjust those scores. So in the first, if P is supported by P prime, so basically P and P prime are, P is from a local trajectory, and P prime is the mapped trajectory from a remote data set. So if they support each other, then we use the following equation. Basically, what you need to pay attention is this part. So if the distance between P and P prime equals to 5, which is the threshold, then this will become 1. And 1 minus 1 is 0. And this part will become 0. Since then SCAS, basically it means that nothing will be updated. And it will become the initial, because on the borderline, we don't want to change the score, because if it equals to 5, we don't know whether whether they support each other or conflict each other. However, if dp and p prime is less than 5, then we can say that they really support each other. Then this part will greater than 1, and this will less than s initial p prime, and the result will increase this initial s initial p. So in the second equation, if p is conflicts p prime, let's again look at this part. So if distance between p and p prime equals to 5, then this one will become 0, and the whole thing will become 1, and SCSP will equals to S initial P, which means it doesn't change, because again, if it's on the borderline, then we don't want to update its score. However, if it really conflicts, P and P prime really conflict with each other, then this part will be greater than this part will be greater than 1. This part will be a positive number, and then we will have a positive number from this part, and this number will be less than 1. So S initial P will times a number which is less than 1. So in the end, we decrease the score of S initial P. So which makes sense because if we find someone supports position P, we increase its score, and if it's conflict with P, then it decreases the score. So next, let's look at the experimental evaluation part. So in the experiment, we use a data set which contains 17,320 points and totally 2,675 trajectories. Actually, it's a track data set recorded in Athens. The total, if we use a circle to bound all the positions for these points, the diameter of this circle is approximately 50 kilometer. And here's the parameters that we use in the example. So the diameter of anonymized tube is from 200 to 2,000 meters, and K is from 5 to 50. Completeness ratio is 20% to 100%, and distortion percentage is 5% to 30%. The distortion percentage here means that how many magnitudes we introduce, how many magnitudes of the fake value we introduce in the data set. Because we don't really have a real fake data set. So what we do is that we modify the real data set by introducing some random fake values. We use this distortion percentage to control how large the fake values we introduce in the data set. Complete ratio means that what is the number of points, what is the number of trajectories contained in the remote data set. And we evaluate based on the following criteria. Basically, how much score increase for the correct data and score decrease for the incorrect data. So this is the running time for common pattern analysis. We can see that even the completeness ratio is 100, which means we deal with about 17,000 data points. The running time is about like 12 seconds. It's very fast. And the execution time for the confidence support is even better. The reason is that for the confidence support analysis, we need to first divide remote data by equivalent classes. So the data set is kind of small. So we only need several hundreds of milliseconds to complete the algorithms. So let's look at how the K values impact the results. So we can see that when the K values increase, the gap between the average scores of before we introduce the remote data and after we introduce the remote data becomes smaller. The reason is that large K value actually introduce more translation errors. So the remote data set becomes more and more imprecise, and it's more and more unuseful. That's the reason you can see that the gap becomes smaller. So if the K is too large, basically the remote data set would be really not useful. We will discard it in the end. So we actually end up with not increase much. The trust score will not increase much. So the second graph shows the complete. If we increase the completeness ratio, what is the gap between the average score of if we include the remote data and before we include the remote data and after we include the remote data? You can see the gap between those two average score is constantly almost the same, and the 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 both of the average scores decrease. The reason is that when we include more and more data, so because the uh, nature of the equation we use, we have to have this effect. And if we increase the data, what will happen? Actually, the gap increase slightly. The reason is that when the data is large, actually we introduce less translation error. So although the user basically we introduce less translation error, so the gap actually increase because the data we receive from the remote data set is more useful. So the previous experiments is performed on common pattern analysis. So let's take a look at what the conflict support analysis. In this example, we increase the number of suspects, and we can see that increased number of suspects doesn't make much impact on the average trust score of incorrect data and correct data. We can see that the average trust score of correct data is close to 0.75, and incorrect data is close to 0.25. The reason is that we only consider one local data set and one remote data set. So the maximum trust score for the correct data is 0.75. At the minimum of the trust score is 0.25. And we can see that our algorithm can easily distinguish distinguish incorrect data from correct data. So, but still, there's some small difference between the basically, if you see that when phi equals to 5%, the trust score is lower than the phi equals to 20%. The reason is that when you so basically when you introduce less error, so phi controls the magnitude of fake values we inject in the data set. So if we introduce a small amount of fake values, actually it's difficult for the algorithm to distinguish the correct value from the incorrect value. So this figure shows if we change the distortion percentage, what is the effect? What is the effect of the performance? So it's a very interesting figure. So if we see, so basically distortion percentage means that means that how many what is the magnitude of fake value we inject in the data set, and for each line, for example 5%, it means that we use phi equals to 5% to distinguish the correct values and the incorrect values. We see that at the very beginning it's difficult to distinguish. The reason is that we use 5% distortion percentage, and if we use phi as the 5% as the threshold, we can distinguish some of them. So so if you see the rectangle line, it's 0.5. The average trust score for the incorrect data is 0.5. However, if it's we use threshold 10% or 20%, because the magnitude of fake value is small, we really cannot distinguish fake values from the real values. So so everything is close to 0.7. However, if we increase the distortion percentage, which means that we increase more more magnitude of fake values. When it reaches 20%, at that time, the 5% line and the 10% line already close to 0.25. However, the 20% is still it drops to 0.5. And if we keep increasing the magnitude, in the end we can identify all the fake values. So, in this paper, we propose anonymize. We can see that our conclusion is that anonymized data can significantly improve trustworthiness assessment accuracy. And we propose two techniques. One is called common pattern analysis. Another one is called confidence support analysis. And for the future work of this research work, I want to actually adopt more privacy models like differential privacy. The reason is that K-anonymity privacy model is considered to be weak with respect to privacy requirements. And differential privacy model is a more strong model. So we really want to adopt that model. And we want to take the factor in the road network characteristics because that in the current research work, we only consider trajectories. We only use those trajectories to compute the common pattern. However, we know that if there doesn't exist a road, we cannot move from some of the paths may not, some of the trajectory is not realistic. So if we use road network as an additional piece of supporting information, it will be interesting to see how the trustworthiness model changes. Any questions?
So we have some time for questions. So do you have any questions? Okay, so perhaps since we have still 5 minutes, can you discuss whether this type of trustworthiness assessment can be applied to other types of data other than location data?
Okay.
For example, social network.
Yes. So definitely those type of techniques can be used to apply on some other data, other kind of data. For example, social network data. So suppose you have, let me give you an example. So suppose we have a local insurance company. So if those, I know that some of the local insurance company will give you, so for example, you are already a customer. It may provide you some incentive like discounts. For example, if you bring some new customers to the company, it will give you some discount for its insurance policies, for example. So through these incentive techniques, it can form a local social network. For example, Bob introduced 3 of his friends to this company, and the company can know, okay, because they are recommended by Bob, they must know each other. And after a period of time, after this procedure continues, it can form a local social network. So when the reason that those companies may want to have this local social network is because so sometimes the policies, the money that you need to pay for the insurance policies may change depending on your location, age. For example, if you are older than 25 and your location is in Indiana, then probably you just need to pay $100 for 6 months for your car insurance. But if you are less than 25 and maybe you are in California, maybe the amount of money you need to pay is 2 or 3 times, maybe $200 or $300. So because of this reason, so the the customer who, enrolled in a new insurance policy may fake their, um, some of their um, profile information. For example, age, location, maybe marriage status, or maybe education level. So some of them may be easy to detect. Other may not be very easy to detect. For example, I can move to California to stay for a few months and get some like bank statement and use that information to get a cheaper insurance policy. Then so the motivation for the insurance companies to use uh, to verify the local information, but the only thing he has is a local social network graph. So, um, but we already have large social network. Uh, for example, Facebook uh, and LinkedIn. Those large social network. Those social network may contains real values of someone's attributes. For example, LinkedIn. You don't want to fake your education level in LinkedIn, right? So uh, so, those social network can be used to verify the local social network. However, again, the challenge is that for those big social network like Facebook, he cannot just publish his data because that will definitely violate the privacy laws. So the only thing he can do is that to publish the anonymized uh, social network that preserve the privacy. So the challenge will be how to make use of the anonymized social network to verify our local social network.
There are other questions? If not, thanks.